Right. Now, before you can start in the day school, have you got access to the uh, LMS or ULMS, the course? Have you logged on to it and see?
Yes, sir.
Okay. So, and some of the students have not got the access. So we try to log in and stay there for a few minutes, and sometimes the automatically the system will give you the access. If not, just send me an email so that I will forward it to the IT division for your enrollment. Now, I have got one or two emails. Please see whether you get the access, because I'm going to link the day schools, the recordings, everything to the LMS and the day school link also. And I'm using the same day school link for the all day school. So if you have one, that will be it. Right. So we will move on to the class. So actually, when we learn about the operating systems, main thing that you need to handle is the processors. So processors are almost all the runnable software on the computer, including operating system, are organized into number of sequential processors. Processors means one task which is running or staying idle in the computer. So the each process is having so the process is activity of some kind, and it has several components. First is the program, but what it is doing. The second one is input uh, of the I mean the data and various other things that is needed for carrying out the task. And the output means the after the task is finished, what is the output. And a process is having a state. So this state means whether that process is actually running on the CPU, whether that process is waiting for some other um, input output operation, whether this process is suspended because of a higher priority job that is running, and so on. There can be a state to the process. So because of that, these several states can be there for a process. So let's see. First of the all, we need to, I mean, create a process. So when we want to create a process, uh, there are several activities that can be there to initiate a process. First one is initialization of the system. That means when you turn on your computer and it when it boots up, so the operating system uh, will create multiple processes so that it would be there for you to see. uh, different processes are being started and running. Then afterwards you will get the login screen. So in between that, several tasks has to be carried out. Operating system has to load and all those things. So for that you have several processes are created. So that is why, as a first point, it has been said that initialization of the system will create multiple processes. Then the second option is when a running process execute the process creation call. That means one task, when it is in the middle, it may be needing some other task to run, and another process can be created. So that is the second one. The third one is a user program or process request to create a new process. Now, for example, if your word processor like Microsoft Word running and it need to initiate say spell checking operation, so it need to initiate say printing operation, so that sort of different operations can be created as new processors. So when that happens also, processors are created. Then the fourth option is batch job is initiated. Now, for example, now if you are in a multimedia industry, there can be several videos need to be edited. Then those things has to be rendered as a single video, and this joining process has to be done. So that sort of a big task can be initiated by a software, and that uh, s- has to be run for hours. So this kind of a batch job is initiated also. Several subtasks like um, framing, annotation, and various other jobs has to be done. So those are kind of a different processes. So all those four steps uh, can be there when a new process is created. So this uh, uh, is creation of a new process. So when I ask you at the examination, uh, when can a process be created? So you have to give these four uh, um, options. So, and this is sort of a theoretical question that has been asked for several years. Uh, that I can't say this time also I am asking, but so this is a possible examination question. So then we move on to the types of processors. What kind of processors that are there in an operating system? So there are two types of processors. One is called foreground process. Foreground process means the process which interacts with the user. Uh, Now, for example, Microsoft Word, Microsoft Excel, the video player, all those software which is run as a process are interacting with you. So you give different commands and it will act upon what you do. So that are called foreground processes. Right. Then the background processes uh, are sort of processes running on the background, which is not directly interacting with the user, but it may be having some specific function. For example, the virus guard or spell checker. So those are not directly interacting with the users, but runs on the background. So those are called background processes. Now, when it comes to a creation of a process, the Windows operating system and the Unix operating system and the Linux operating system, two families of operating systems are having different commands. In the Unix, you have a command called fork to create a process, and on Windows, you have create process command. Uh, to create a process. So these are actually system calls which we have learned, which can only be initiated through the support of the kernel. Then we need to know what is when it is the time when a process is terminated. That means it will either exit or abnormally terminated. So this will there are four types. First one is called normal exit or end. That means when a task or a process is started and it has finished its work, then it can automatically close out. So we call it normal exit. Then the second type is error exit. So that means when the process is going on, there is an error. Maybe it can be either input output error, or it can be maybe user has input the wrong data or something. or the process cannot continue. So then it will exit by giving an error. So that it cannot continue. So that is the second type of terminating a process. The third one is called fatal error. Fatal error means some kind of a error in the program or some kind of a error in an environment provided by the operating system, or based on a system error, program cannot continue. The task, the process cannot continue. So we call it a fatal error. So that means it is not related to input output, but it might be related to error in a system or error in a program of a process or some kind of a systematic error. So because of that, the system cannot continue. So it gives us a big red background circle with a white cross, giving a fatal error message, and it exits. So that is the third option. The fourth one is when a process is terminated, it can be killed by a user or another process. So that means we think that okay, this process is not needed, or it has hanged. That means it is running forever but doing nothing. So then user can terminate the process. So we call it a kill. So otherwise another process can terminate the running processor. So either of this situation, the user the process is can be killed. So therefore this is another task. So these
Sir,
four,
excuse me.
yes.
Sir, can you please explain about a fatal error again?
Fatal error means because of a system program error or a error in the environment, like other processors are not allowing this process to continue, there can be a error coming out of the process. So that is not related to user errors or not related to input output, right? So because of that, the fatal error can come. So then it will give out a, if you have using a Windows user, you might see is abnormally the system comes out a message, gives a message saying that fatal error with a this cross in a red background comes, and fatal error, the program terminates. So that kind of a exit is called fatal error based exit. It is not because of normal input output error or a uh, exit by a user. No. So these are two types of errors. 2 and 3 are two different things. Second one is actually based on the input might be invalid. For example, if you want to input a number, user has accidentally input a text. So that can be a normal error. So it gives us that error command and it can exit. So that is a normal error exit. Okay. So then the most processors these are the four types of exits that can have for a process. Then most process terminate because of a completion of work. So that is the first option. There can be errors caused by the user or process itself, the 2 and 3. And the final one is killed by the user. So the Unix function, there is a kill command, and Windows, you have a terminate process system call to terminate the processes. So these are the four types of termination which can be there in the process. So the hierarchy in the process, that means when process creates another process, the first process, it can be a parent, and the second process created can be a child. So this will create a hierarchy. So there is a one process which creates another several sub-processes. So the first process is sort of a parent, and the other processes are sort of a children. So it can be a parent-child hierarchy in a system. So in Unix, this process and its children create a process group. So this thing is parent cannot disown the children. That means if the parent process will trying to separate the sub-processes from its parenthood, it cannot be, it is not allowed in Unix. So therefore, when one process creates another process, there is always a link. But in Windows, there is no concept of process hierarchy. All processes can be an equal. So even though one parent will create another process, still those are considered as two different processes. But there is an maybe an special association, like when a parent creates a sub process, there can be a special association like linking a process, but it is not directly parent-child sort of relationship. It says there is an association. So that there can be a sort of a similar grouping. So therefore, you can send data between those different created processes. So a new version of Windows, like Windows 7, you have a process tree, which is almost similar to the Unix system. The main process can be associated with the other sub-processors, but still there is a no direct parent-child sort of a relationship as in Unix. Next thing is the state of a process. Yeah, wait a minute. Right. So there are two questions asked in the chat. I will answer before going forward. So one is called a kill command for Linux, purge all. Yeah, the purge all means the killing. I mean all the related sub-processors with the parent, but the main command is called kill, right? So that is the Unix command. And the second question is, sir, what is KB activity in unit? KB means keyboard activity. Okay, so that's the answer, right? So then we'll go forward. This state of process is very much needed when you, I mean, have a process in the system. So when a process executes, it goes through a discrete state. First one is actually when a process is created and it is ready to run, it says we call it the ready state. So this is the initial state of a process. Then the system manager, we call it a dispatcher. So this it will schedule the ready processes in the list into a running process when it is given the CPU time. So we call it running state. Then when the running state process maybe waiting for an input and output, say like reading from a keyboard for a user input, or waiting for a to read the hard disk and get some data, or waiting for some other process. So then the running process will be sort of a moved on to the block state because it cannot utilize CPU. So the running process actually move on to the block state and allow another process to run on the CPU. So the running process can be there put onto the block state. Then when that particular input output operation or keyboard input or whatever the other waiting for another process output that has been received, then that process can be moved back onto the ready state so that it can wait for CPU time. So this cycle, this three-state cycle is there for a processors. However, uh, including these three status, there can be another two states that the process can be there. We call it process state transition. So this is the diagram that is mostly asked at the examination. So we call it process state transitions. So and there are keywords associated with it, so that you need to know this. So we will start from the beginning. First one is the new. New means new state means the brand new process is created. So it is newly admitted to the system and that will be there in the ready queue, right? So when there is a ready queue of processors, the system manager, the operating system is picking a process uh, based on the priority or based on the incoming order or any other mechanism to run a process in the list in a CPU. So when the process in a ready queue is allocated CPU time, we call it running state, right? So when a running process is interrupted in some manner, right? So it can run, but somehow interrupted. For example, now think about a photocopy machine, right? So if you are, your book is getting photocopied and it is about 300 pages job, and suddenly another person comes and say, I only have one page. Can you allow me to, get this thing photocopied? Then you sometimes give that chance. So then your job can run, but there is a higher, a shorter job or a higher priority job has come. So what you're saying is your job is interrupted. So your one is again put onto the ready state and that another process will run. So when that happens, we call it interruption. So interrupted, then the process can be there put onto the ready state. And when that task is over, you can again put it to the running state. So that is called interruption. So there is no other blocking, but you simply put it into the ready state. Then another thing that can happen is, as I have explained earlier, is it is waiting for an input output or a wait event so that the process cannot run. So then from the running state, it can move on to the block state. So there can be a list of processes that are blocked because of waiting for a user input or waiting for a IO input output event or waiting for another process to give some output. So then it will wait. Then that output is received. That is, that event is completed. It can be again put onto the ready list, waiting for a CPU time. Then after running the process, it can be either terminated uh, using that 4 steps. It can be it can finish the job, or it can be killed by a user, or it can be an error exit, or anything can happen and it will terminate. So these are the 5-state process transitions diagram that have been asked several times um, for the exams. So you should be able to explain how this works, right? So that's the one aspect of it. So these transitions that I have explained are having a different names. So these are the 4 different names. First one is the dispatch. That means when a process from ready state to the running state transition, we call it dispatch. Okay. So that is the keyword, right? From ready state to the running state, right? Then the second one is timer run out. So now the modern operating systems, uh, when there is a long running processors, list of processors are there, you can give a sort of a small time period for each and every process to run. We call it the timer. That is process CPU time can be given for each and every process. So when that his chance comes, that process can run. When the time is over, it has to either go to the ready queue, or it has either maybe waiting for some other input and output. So that sort of time the CPU slot can be given. So everybody get a chance. So then that sort of activity happens. We call it timer run out. That means the process is has got some CPU time. It has run that within that CPU time, but still there is work remaining. So then that process is interrupted, then it again waits for its next chance, right? So then it is moved back to the ready state and it waits. So that is called timer run out. That means changing the running state to the ready state. Then the third keyword is called block. So that is running state to the block state. So that I have already explained what the block state means. Then the final one is called wake up. That means after a block state, whatever has been resolved, it is moved back to the ready state. So we call it wake up. So that means block state to the ready state. So these four keywords are essential uh, in this explaining the process state transition model, right? So only the state transition initiated by a process is called block, all others initiated by the external parties. So that is a fact. That means it whether when it comes to waiting or waiting state, and then that is a process. Now, for example, it is waiting for an input output. So it is waiting for reading from the hard disk. So that is initiated by the process. But the other things like moving the running state to the ready state, um, and, and the wake up, that is completing the job and putting back into the ready state, all those things, giving the CPU time, all those stuff, all those tasks are handled by the other parties like external manager of an operating system. So we call it a dispatcher. So that is one theoretical aspect that you need to know. Then, what is process control block? Now, actually, now you have learned that there can be many states for a process from its creation to its termination. So the creation, after creating a process, that processes state the variables, the memory allocation, and which state that process is in, and all those information has to be recorded and tracked by the operating system. Otherwise, it doesn't know which state, which process which is there in the system, and whether it is a running state or a waiting state, how much resources that has been allocated. So all those things has to be somehow stored. So that is the process control block is the place where those information is stored. So and all the processes that are there, which is running or in a ready state, uh, is they are in the process table of an operating system. So first of all, we have a list of processes which is there in the process table, and process descriptor is a basic data structure used to represent the state of the process. So this process descriptor, or otherwise process control block, is the name given for storing this intermediate information about a process uh, with respect to the operating system. So sometimes I have asked this question, give some the different fields that is there in the process descriptor, right? Then people have not written anything because they have forgotten that process descriptor is a another name for the process control block. We have learned about the process control block, but they have forgotten that the same name, process control block, is called the process descriptor as well. So that is what that you need to know, that there's different names, and the with that, this process control block contains several fields, because it is the place where all the information required to save a process when it is suspended or stored. That means if you have a state written there, then you can just take that process out of the CPU and keep it somewhere until it gets the CPU time. So when these processors, different processors switch between CPU, this is very much essential, right? So these are the different fields that is there in a process descriptor or a process control block. So it's a basic data structure. So first of all, it has processor registered contents at the time of the process that was last suspended. That means yes. So somebody talking, right? So the process, first thing is the registers of the processor, those content of the registers which is there when the process is suspended, that is has to be there in the process descriptor. And then the unique identification of the process, that means a process has been given, should be given a process ID. So using that ID, we can kill the process. Example, if in the Unix, actually when you list the process, it will given the process ID, the number. So then we give the command called kill with that process ID. So then that process will be terminated. So likewise, the process descriptor or process control block has unique identification of a process and its state, whether it is suspended or it's running or the other states, and the address space of mapping details. Now, for example, address space means the when a process runs, its data has to be, they are stored in the memory, different places, and in the hard disk at all. So those different addresses has to be stored in the um, process control block. And its memory state, how much memory is allocated, and then the pointer to its stack. Stack means uh, intermediate data. Now, for example, you want to do some calculation and there are multiple steps. So I mean, when you do a calculation of each step, the intermediate variables can be there stored in a stack. Stack is sort of a place where you do some intermediate calculations and get the output. So the intermediate data is stored on the stack. So that pointer to that particular stack has to be there. And what are the resources that has been allocated to the process, and the which processor number that is running. So in that is very important in modern computers, where multiple cores are there. So which core this process is running, and the CPU registered input output status and the scheduling data all has to be there in the process descriptor. So in the book, I have given this the entire set of fields with the descriptions. So I urge you to read them, because there might be examination questions on this particular area. Then we move on to the next slide. So when the operating system is configured, it has a fixed number of process descriptors, represents the maximum number of processes it can support at one time. So that means the number of processors which are running on the system cannot be unlimited. So that means these processors actually has to be there when it comes to the uh, operating system, the number of processors which can be stored and running at the time. So generally, this is a large number for a modern operating system. However, there is a limit. And the process descriptor is allocated when a process is created, and process descriptor is released when the process terminates. So that means it has to be reusable. Otherwise, when one is allocated and it has allocated forever, that means then the number of process descriptors that can be used will end after some time. So that will not happen when process terminates, that particular space is released. Then the process manager manages the process descriptor, and however, the operating system can change the field based on the work that is being happening inside the process. So these are the different uh, fields. So this is actually the descriptions that is there in the book. So I will invite you to read it. Now, how the CPU is switching from one process to another process. This is very important. Now, see how we will read this diagram. Okay. So the operating system is in the middle. So this is from top to bottom via the time. So there is a process P0 is running. So it is executing. It is executing means it is running on the CPU. Now, how that is switching to the process P1, which is given in this particular diagram. So when it is executing, suddenly you get a interrupt signal, so that you have to stop. So what it do is the running process P0 will save the state onto the process control block 0 with the information that it currently has uh, in the PCB 0. Then after some time, then the CPU is released, right? Then after the saving is over, then the process P1 state will be read from the whatever the place it is stored onto the CPU, and it is reload the state, and then it will start running on the CPU. So then the P0 state will be saved, and the process P1 state will be read onto the memory, and it will be allowed to run on the CPU. Then it will be running at the CPU. Now, until this time comes, the process 1 stays idle, right? Then after after P1 has running, then it may again get a system call saying that, okay, your time is up, so you need to give back uh, the CPU to the CPCB, the process P0. Then it will stop and it save its current state in the PCB1, then reload the state from PCB0, which is stored earlier, and it will start running. So this is how the process process switches between CPU. First it save the state, then it will reload the other process time, and then it starts running. After time it allocated is over, it will be given to the save state back to the PCB, which is stores this information, and the running processors will be loaded onto the memory, and it will start running. So this is sort of how the switching mechanism of processors between CPU is initiated. Then next important fact is how the process scheduling is done. That means there are list of processors in the ready queue, and which process is allowed to run on the CPU. So when there is a need for running multiple programs, actually these days we need to run a lot of programs in parallel. So we call it multi-programming operating system. So but only one program can run at a time in the CPU. So
So excuse me.
yes.
So about process, can you explain again?
මොකද්ද?
So අර උඩින් තිබ්බ මේ process එක ආයෙ මේ explain කරනවද? ඒක
ඇයි
හරියට තේරුන්නේ නැහැ sir.
ඒ කියන්නේ මෙහෙමයි. Now the thing is now there are two processes. One process is running on the CPU, right? So we need to switch to the process 2. Okay, so what it does is the currently running process will be stopped at particular moment and its state is saved. So we call it saving in that particular PCB. හරි, ඒකේ තත්වය අපි save කරගන්නවා තැනක, right? Then we save that particular state and then the CPU is idle. Then the second processor's information will be loaded to the CPU and the registers. So we call it reload in the state of the PCB1, right? Then it will run. එතකොට දෙවනියාගේ information load කළා එයා run වෙනවා, right? So when that second process is running some time and it's say its CPU time is over, then it has to stop. So what it does is its current state is saved onto that its PCB and handed back the time to the CPU. Then CPU will load the next one, which is process P0, and it reload the state from the PCB0, which is saved here, and it will run that time. So that is, you are just switching. When you are switching, you save the current state. ඒ කියන්නේ වැඩක් කරගෙන ගිහිල්ලා එයා නැවැත්තුව තැන ගැන මාක් එකක් දාගන්න. දාගෙන අනිත් එක්කෙනාට වැඩ කරන්න දෙනවා. අපි හිතමු එක මිටියයි තියෙන්නේ කියලා. I will tell this in English. Suppose you have only one hammer, right? Right? It is called CPU. So there are two tasks which is needing that hammer. So then one person uses the hammer, and at some point, okay, that it says, okay, person one, okay, you have to stop, and you have to give that hammer back to the person two for his work to do. So that what it does is karana vade, that the task it is doing has stopped at some moment and it is saved. Okay, that all the work that has done so far is stopped at that time, and it's saved in a particular PCB, and that the control is given to the other process, so that second person uses the hammer from the point where it stopped earlier. So it loaded the thing, put that into the workbench, and it works, right? Hammering is done, and after some time, okay, its time is out or time out is happening. So it says, okay, now your work has to stop because I have to give that hammer back to the other person. So it does it, it's save the state, take all the work from the maybe memory into some other location and free up the space, workspace. Then the first person again given the chance, so he takes his work back to the CPU and starts continuing. So this is sort of a, I mean, real world situation. We share the CPU between processors and we save the states of the process which is there at the time in a PCB. I hope you understood the thing.
So I got it. Thank you, sir.
Right. So then the CPU time actually shared across multiple programs, and we get an illusion saying that all are happening at the same time. So that's a beauty of the operating system. Now supposing you have one CPU and it is running fast, I mean so fast, and what you do is your multiple processors, you divide that CPU time into process 1, process 2, process 3, and so on, and give that part of the CPU time for each process. So each process then actually runs on the CPU. However, after some time, the switches control back to another process. Again, after some, it gives the CPU time to another process, and so on. So everybody works sequentially, but they complete their jobs little by little. but it is happening so fast that we will have a illusion thinking that all are happening at the same time, right? So that is why in the modern computers, you would see that while you are typing something in Microsoft Word, sometimes you can listen to the music, and sometimes there can be virus checking at the background, and some other task is processing at the background. So you will feel thinking that all are happening at the same time, but what actually happens is it will work, each process works one after another, but it is happening so fast, the switching and the everything happening so fast that we have sort of illusion that everything happens at the same time. So this scheduling, that means which process runs next on the CPU, is sort of a problem that is there uh, in the same time. Somebody asked about multi-threading. I will explain that also, uh, because there is a separate topic for the threading, but I will explain when since the question is asked. So, so that means, so in a CPU, the one process can run at the same at a one time, but when there are multiple cores, sometimes you can schedule the processes in different cores that so that those can execute at the same time. So the modern CPUs are capable of having multiple cores. So this concept of one task at a time have a little bit diminished now these days because of the multiple cores you have. However, uh, still certain operating systems give priority to a single process and its children to be run on the CPU, so that every core which is there will be given some CPU time of the same process. So the concept of multi-threading comes there because when a single process creates multiple subtasks called threads, which will share the same data and the instruction stack of a process, then it can run on multiple threads, can run on a different cores, so that it will be completed. But if it is a single CPU which only has one core, even the multi-threading concept, the threads are time shared. That means first thread will get the CPU time. Then after its time is over, second thread gets the time. Likewise, the time is shared between threads. So that is about the multi-threading. So actually there are difference between process and threads means the process is sort of having its own stack, own data, own memory space, and so on. But in a threading situation, which is created by a single process with multiple threads, all the threads share the same address space, same CPU, and the um, data set and the address space of the process. So it is sort of a lightweight processes which are linked to each other, threads. So we have a separate session on that. I mean the section on that you have to read also for the fat one, I think. So that is the difference of the process and the uh, threads and the processors. So we'll go back to the scheduling. Uh, Scheduling is not a problem in batch systems because they in a batch system, one job does after another job. Next job is scheduled after one job is finished. So, but in a multi-programming environment where multiple processors are competing for the CPU, then it requires a good selection. Okay, which one goes next into the CPU, right? There are multiple people in the queue. So which one is given the chance to run, right? So that's a good question to solve. So there are different, I mean, mechanisms. We call it process scheduling algorithms in order to do this job, right? So in pieces, there are some active jobs by user at one time, and others have to be waiting until the person who gets the chance is working on. So there are two types of processors actually. One is called CPU intensive jobs. That means that processors always need the CPU time. Then the other types of job is IO intensive jobs. IO means input output. That means it always want to read from somewhere, read from this, read from CD, read from USB, or read from network or somewhere. I mean input output intensive. So that sort of two types of jobs are there. So then when we have a mix, then we can balance this out, because while one process is waiting for input and output, we can give some time to the CPU intensive jobs. So there is a mix. So the scheduling is so important that uh, because if you properly schedule these jobs onto the CPU, you can achieve the maximum output within the given time. We call it throughput. That is, throughput means the number of jobs completing at a given time period. So if the number of jobs completing at the given time period is high, that means you have a higher throughput. So these are the several factors that is affecting this CPU scheduling. First one is called CPU's utilization. That means the how much time that is CPU actually does running the programs. So we call it CPU utilization. So if it is 40%, it is called a lightly loaded system, where 40% of the time the CPU does the job, and other 60% it's in idle state, where any new processors can be scheduled at that time. But if it is utilization is 90%, that is we call it a heavily loaded system, where only 10% is there for the switching between processors and all. Right. So give me a second, please. So then the next thing is, if it is a lightly loaded, we can actually have more time switching between processors and all. But if it is 90%, that is heavily loaded, that means only 10% of the CPU time is there for the switching and all. So that when it is highly loaded, that is around 90% loaded, then the users will feel that, okay, system gets slowed down, because there's so many processors that are running, and the response time for the user will be little less, so that that, okay, system getting slowed, the tasks you give will be waiting without actually running. So that's sort of highly loaded. So the scheduling, you have to take the scheduling decision of new jobs, putting back to the CPU. Then it is important to consider the utilization of the CPU. So at the time, then the next thing that you need to think about scheduling is called throughput. That system utilization, that is the number of jobs that are completed within the given limit. So throughput I have explained. Now the number of jobs completing at a given time uh, has to increase when you take the schedule decision. So if the number of jobs completing getting reduced when you take a scheduling decision, then you need to think twice before scheduling that job onto the CPU. Right. So that is the second point. The third point is the turnaround time. So the time for the job completion. So if you are scheduling a long running job with short running set of jobs, then you need to think on balancing how you allocate time of the CPU to these different jobs. So the turnaround time means from the time from the admission to the queue until its completion. So the what is the number of milliseconds or seconds that will be spent on the system before completing, right? So that is called turnaround time. Then the waiting time. So when the CPU works with the multiple jobs, one job runs at a time, others has to wait. So this waiting time, if it is a larger number, then actually processors are the process is waiting in the idle situation without actually doing anything important. So this waiting time has to be minimized when we are scheduling the jobs onto the CPU. And the final point is called response time. So response time means so from the admission to the queue until it gets its first CPU slot, the initial waiting time, right? So response time is different than waiting time because the response time is called from the admission to the queue until it gets its first CPU. The time waiting in the queue is called response time. So that these different factors are affecting the scheduling decisions, which jobs goes next to the CPU. So let's now these are a lot of theory that we have learned. So and these are the two different factors. In an interactive system, it is suggested that important to minimize the variance in the response time than minimizing the average response time. Yes, that means if a job goes to the queue and you know that, okay, within 5 seconds you get a CPU time, then you are happy, right? So that initial response time has to be minimized. So, and some jobs get a response within 5 seconds and some gets after 5 minutes, then you have a problem because you cannot guarantee that the within a given amount of time you get a response from the system. So you have to minimize the response time when you are scheduling the jobs in the CPU. And in a uniprocessor system, uniprocessor means a single processor which is having one core. There is only one running process at CPU. All others have to either blocked or ready queue, which is a sort of a linked list. So you have learned this about this linked list in your data structures on the first year. Hope you know that what a linked list is. That means it's sort of a list with uh, pointers from to top job and the bottom slot. So that sort of a list is maintained when it comes to the ready queue, right? Now this scheduling jobs are sort of two types. One is called long-term scheduler. The second one is called short-term scheduler. And sometimes you have medium-term scheduler also. So the long-term scheduler, we call it job scheduler, determines the which jobs are admitted to the system. That means if you have multiple jobs there out there, then which are being actually getting admitted to the ready queue even, right? So that is called long-term schedule because there can be jobs, uh, but we are not admitting them to the system because the ready queue is full, right? So then the short-term scheduler is called CPU scheduler, where responsible for allocating CPU time for a selected jobs from the memory which are ready to execute. That is from the ready queue, we are picking up the jobs. Now there are two different things, right? Admission to the ready queue is by the long-term scheduler. And from the ready queue to the CPU, we have a short-term scheduler, right? Right. So now these things you can read from the book, right? So I will skip. And in the medium term scheduler, uh, sometimes when the system memory, the primary memory, we call it RAM, is not enough, we might move those entire processors along with this memory request memory systems into a special area in the disk called virtual memory. That means we allocate a disk space which act as a additional memory space for a RAM. So we call it virtual memory. So when we are moving the processors from the main memory, the RAM, to the virtual memory, which is part of the disk, we call it, swapping. The swapping operation is handled by the medium term scheduler. So we will discuss about these different schedulers when we actually do the algorithm. So let's move some work into the scheduling algorithms now. So this comes the interesting part, right? Now we have learned a lot. From 9 a.m. onwards, I am talking, and about these different uh, different aspects of the process scheduling. Now actually then we move on to the scheduling algorithm. Okay, now there are jobs in the ready queue, and how do we schedule it into the CPU? The first algorithm is called first come first served algorithm. This is happening every day within your real life also. You are in the queue to buy something, so then first come will get the first chance to buy something. So that is similar happen to the CPU also. When a job is admitted first into the ready queue, it will get the CPU time first. So first come first served scheduling is the first one that is there. Now remember this this kind of scheduling is very much needed in a CPU, and it is happening. And let's see how one sort of a question that is coming. Now, listen carefully. Now, this particular table you have, the first column is called processors. So, process numbers is there, P1, P2, and P3. The second column is called burst time, that is number of milliseconds which is needed to complete that job. Okay, milliseconds or seconds. Generally, we call milliseconds. So, process 1 needs 24 milliseconds. Process 2 needs 3 milliseconds. Process 3 needs 3 milliseconds. Now, the order of input is given in from top to bottom order. P1 came first, P2 came second, P3 came last, right? So, this kind of a diagram, the table will be given to you, right? So, then you need to organize this thing into a diagram called Gantt chart, right? So then we can easily answer the questions we have, right? So the first thing that we draw is starting from time 0, P1 came first. So we start, drawing the Gantt chart, and P1 is given the time of 24 milliseconds. So P1 gets 24 milliseconds of time. So remember that at the exam and when you are drawing also, not much of a big scale is required. Now, for example, you don't need to, actually have a big space for a scale space using a ruler for a P1 for 24 milliseconds, and the same scale for the P2 3 milliseconds, and same scale for the P3 3 milliseconds. We don't need, just draw it and have some additional, if the P1 is larger, have some little bit larger slot. That's all. Some people will think that, okay, I need to draw it into the scale. No, I don't expect that, right? You just simply draw the chart. So the Gantt chart is drawn like this. P1 came first, so starting with time 0, then P1 is given 24 milliseconds under the first come first serve. Then after 24 milliseconds, the second in the list is P2. It will be given 3 milliseconds of CPU, and P3 is given 3 milliseconds of CPU. So this is the Gantt chart and the order and the times which is needed. So this Gantt chart can be easily drawn for the FCFS like this. So remember that when you have been asked to draw the Gantt chart, you have to only draw the Gantt chart. You don't need to do other calculations. Some people have, to save the time, for the students. Sometimes at the examination, I have only asked to draw the Gantt chart. But, people have referred the all past question papers and they have drawn the Gantt chart as well as, trying to answer the hypothetical questions like waiting time, response time and all. But I have never asked that. So first of all, when you are at the examination, you have to read the question carefully and answer only the things that I ask. Okay, don't waste time, right? So that is the first advice I will give you when the workout questions, because sometimes the question might be similar to the last year's question, but the things that I have asked might be different. Okay, so remember that, read the question before starting the answering the question, right? So then we will see about how to calculate the waiting time. So the definition of waiting time is when the process is admission to the queue, how many milliseconds or seconds it has waited in the waiting queue until it completes the job. Okay, so that is the definition of the waiting time. From the admission to the queue until it completes, how many milliseconds it has waited uh, for getting the CPU time, right? So that's the definition. So let's calculate one by one. For the P1, it came first and it has been given time first. So as soon as it came to the queue, it gets the CPU. So P1 haven't waited for any milliseconds. So P1's waiting time is 0, right? Then P2 came second at the 0 milliseconds, but P1 already came. So P2 has to wait until 24 milliseconds to get the CPU. So P2's waiting time is 24 milliseconds. And P3 has came at 0. However, it has to wait until P1 and P2 completes. So it gets its time at 27 milliseconds. So the P3's waiting time is 27 milliseconds. And the average waiting time is, we add the waiting time of P0, P2 and P3. Sorry, P1, P2 and P3. And then we divided by the number of processes. So that is 51 divided by 3, 17 milliseconds. So this is how you calculate the waiting time. Right. Now, supposing the process arrived in a different order, right? Earlier order is P1, P2, P3 order. Now, supposing that order has a different order. P2 came first, P3 came second, and P1 came last. So the Gantt chart then will be like this. So P2's time is 3 milliseconds. Then P3's time is another 3 milliseconds. And P1's time is 24 milliseconds. It will be given at the end, right? So if you calculate the waiting time, so for the P1, actually, it has to wait for 0 to 6 milliseconds. So 6 milliseconds before getting the CPU. And P2 came first, so it will get the first CPU. So its waiting time is 0. And P3 gets the CPU at the third millisecond. So that is its waiting time is 3 milliseconds. So the average waiting time is 3 actually. So if the order is different, actually the waiting time is lot less. The earlier it was 17, now it was 3, the average waiting time. So much better than the previous case. So actually this is the problem of first come first served scheduling algorithm. When the long running jobs comes at first, then the shorter jobs has to wait for a long time to get the CPU. We call it convoy effect. Okay, short processors are behind long processors. Then it has a convoy effect. That means the short jobs has to wait for a long time to get the CPU because of the long running processors. Right? So have you understood the point? Right? Have you understood it? So far? Okay?
Sir, excuse me.
Yes.
Sir, first or second method, second method is the best to the scheduling.
No, actually the method is first come first served, but the order is different. Okay? The
Sir,
we,
please
we
explain again.
which one? This one or the second one? Which one I need to explain?
This one, sir.
First one. Okay. So now the thing is this. Don't think much whether this is an operating system and scheduling and all. Think it is as a simple photocopying queue, right? Okay. Now, and keep that mapping that, the simple photocopying queue to this kind of a problem, right? Then it is much easy to understand and you don't have to remember, cram and think. You only need to know the concept. Okay, then you can do any question, right? So our algorithm is first come, first serve. That means if you come first, you will be served first, right? CPU will be given at the first. So the problem is you got multiple processors coming in order. P1 came first and it needs burst time of 24, like thinking, okay, you have 24 pages to photocopy, right? And P2 comes on the second in the queue and it has 3 milliseconds of working time. P3 comes at third and it has 3 milliseconds of working time required. Okay. So the order of coming is P1, P2, P3, right? Then the question that I have asked is calculate the average waiting time. So before calculating the average waiting time, we have to draw a Gantt chart. So Gantt chart, we draw it on the way that it has been drawn, right? So first one is P1 uh, is drawn. So at the time 0, P1 comes and it needs 24 milliseconds. And P2 needing 23 milliseconds. So after 24, we have drawn the P2. And P3, we have another 3 milliseconds. After 27, we allow running P3. So the jobs will be completed in this order. And the time in milliseconds will be shown like this, right? Is that understood? You know how to draw the Gantt chart now?
Yes, sir.
Okay. Now, after looking at this Gantt chart, then we have to know about what the waiting time is. So the definition of the waiting time is that from the admission to the queue here until it completes the job, how many milliseconds it has to wait. Okay, that's the definition. හරිද? කොච්චර වෙලාවක් queue එකේ හිටියද? ඉතින් එතකොට until its completion, right? So then we take one by one. Okay, so the P1, of course, it comes to the queue at the 0th millisecond and immediately it got the CPU time at 0. So there is no waiting time for P1. So that is why it is given as 0, right? Then for the P2, it came at 0, but it has to wait until 24 milliseconds until it gets the CPU. So P2's waiting time is 24 milliseconds, right? And for the P3, it has to wait until 27 milliseconds to get the CPU. So its waiting time is 27. Okay. So when you want to get the average, you simply add waiting times of each and every process. So we add 0 plus 24 plus 27 and divided by the number of processes. So there are 3 processes. So we divide by 3 and you got the 17 milliseconds. Got the point? Meka therunada, right? Is it okay?
Yes.
Now,
Okay, sir.
right. Now, supposing people thought, now this is the order. P1, P2, P3 was the initial order. Now, we thought, okay, change in the order. Now, the new order of arrival is this. P2 came first, P3 came second, and P1 came last. Right? So then based on the new order, we draw the Gantt chart again. Right? The times are same. Right? So P2 came first. So P2 is drawn first. Right? From 0 to 3 milliseconds. And then P3 came. Again 3 milliseconds of time needed. So 3 to 6. And finally P1 came. So P1 is 24. So from 6 to 30, we draw the Gantt chart again. Right? So based on this Gantt chart, if we calculate the waiting time, right? P2 came first, so P2's waiting time is 0. P1's waiting time, if you calculate, from 0 to 6 milliseconds is that to wait before getting the CPU time. So 6 milliseconds for P6, P1. And P3, actually, we have to wait for 3 milliseconds to get the CPU. So we have a different waiting times for now based on the different arrival order. So if you take an average, the average waiting time is 3 now, right? Earlier it was 17, but now it was 3 because of the different order of appearance, right? So it is much better than the previous case. Only change was the arrival order. We have changed, right? So this is a problem of first come first serve scheduling. When a long job comes first, all the shorter jobs has to wait until the long job finished. So this is called, a name is given for this concept is called convoy effect. So convoy effect means long running jobs are coming before short running jobs. So that means, in other words, short processes are behind the long processes. So this is a problem in the first come first serve scheduling. Hope you have understood this first come first serve scheduling, right? Now understood?
Yes, sir.
Right.
Thank you.
Right. Give me 1 minute, please. Okay, let's continue. Now in the first come first serve scheduling, we will learn about another calculations also before moving into the next algorithm. Okay. Now you have learned what the waiting time is. Next, we will learn about the turnaround time. Okay. Turnaround time is definition. Remember that. Definition of the turnaround time is from the time which is entered into the queue until the time it completes the job and finish. Okay. ආපු වෙලාවේ ඉඳලා වැඩේ ඉවර කරපු ඒ කියන්නේ ජොබ් එක රන් වෙලා ඉවර කරපුවා වෙලාව වෙනකන් කොච්චර වෙලාවක් ගියාද? So if I tell it in English, that means from the time to the admission of the queue until it completes everything and leave the system. So that is called turnaround time. හරිද? ඒකට turnaround time එක calculate කරන්න පුළුවන්. So let's do that. So I will draw this annotation. Okay. So now we are going to calculate turnaround time. Right. So based on this Gantt chart, right? So what is the turnaround time for P1? Can somebody tell me? From the admission to the queue until it completes. So when it is admitted at time 0, right? P1 is admitted at time 0. When it is completing at time 24. Yes. So the turnaround time for the P1 is 24. Right. Then for the P2 came at time 0, P2 also, and finished at time 27. Right. So then the turnaround time for the P2 is went at 27, came at 0. So the total turnaround time is 27 for the P2. And for the P3, came at 0, finish at 30, right? For the P3. So the turnaround time for the P3 is 30, went out, came at 0. So the turnaround time for the P3 is 30. So the average turnaround time is, I will use the different color. This color is not right. Average turnaround time is, we have to add all these three together. That is 24 plus 27 plus 30 divided by 3. So that means 81 divided by 3, 27. Yes. Now you know how to calculate average turnaround time, right? Okay, right. Now the next calculation you need to know is the response time. Right. So let me tell first what's the definition of the uh, response time is. Response times is from the admission to the queue until you get the first CPU time. Okay. Remember that. From the admission to the queue until you get the first CPU time. Okay. So that was the response time. So if you take P1, what is the response time? P1 admitted to the queue at 0 and it got the CPU time at 0. So that means 0 minus 0, 0. Response time is 0. Right. And for the P2,
24.
yes, P2 24. P2 is admitted to the time at 0 and it got his first CPU at 24. So 24 minus 0 is 24. And third one, is P3. It admits us to the time at 0 and got this CPU time at 27. So 27 minus 0 is 27, right? So if you add these three together and divided by 3, that means 51 divided by 3 is 17 is the average response time, right? So this is average response time. Okay, so that will be it, right? These are the three kinds of questions that we can ask from after asking to draw the Gantt chart. One is called waiting time. Second one is called turnaround time. Third one is called response time, right? The difference between response time and the waiting time is waiting time is the time it waits for a CPU from the admission until the end, right? For the response time from admission until it gets the first CPU. That is the difference, okay? So turnaround time, of course, from admission until it completes and leaves the queue. That is the time spent, right? So hope you understood these concepts, right? You hope you understood the first come, first served scheduling algorithm. Then we can move on to the next scheduling algorithm. Is that clear, everybody? Right? Is that clear? Right.
Yes, sir.
Right. Okay. So let's move on to the next algorithm. So the next one is called, I will clear the annotations. Right. Then we'll move on to the next one. Then the next algorithm is called shortest job first scheduling. We call it SJF scheduling, right? So the shortest job means associate with each process the length of its next CPU burst. Choose this length to schedule the process with the shortest time, right? Give me a second, please. Right. Okay, let's go forward. So the next thing that we need to do is shortest job first algorithm. So that means there are when there are jobs in the queue, we pick the shortest one for the next CPU cycle. Okay. So there are two concepts actually of the two types of the shortest job scheduling. One is called non-preemptive and the second one is called preemptive. So there are two differences of the non-preemptive. So the CPU is given, once the CPU is given to the process, it cannot be taken out. Now, for example, if the process 1 is given the CPU time, then until it completes its job, it cannot be taken out, right? And for the preemptive one, you can do so. That means, supposing that, okay, 24 milliseconds job has given a CPU time, then it is running on the CPU, and suddenly there is a job with the 3 milliseconds of time comes. So that now the 24 one has already started, but when there is a shorter job comes, it can be, I mean, the long job can be taken out of the CPU and short job can be given the CPU time. So that is called preemptive. So these two schemes can be used to do, because if the remaining time in the CPU is short, is larger than the one coming in, then we can simply okay, you go out, I have a shorter job that I can run, and then given the CPU time. This is exactly like what is happening in a university photocopy queue or something, right? Saying that, okay, when there's a longer photocopying job going on, when one person comes running in saying that, okay, I have only one page, can I do the copy? So then the photocopy man stops our job and the shorter one is allowed to run likewise, right? Then again we have been given the chance, then another person with the 2 page comes running saying that, I have only 2 pages, can you allow me to run? Likewise, you know, the long running job can be preempted or stopped until the shorter jobs are being processed. So if the non-preemptive one comes, the photocopy man can say, okay, even though there are shorter ones waiting in the queue, no, I have to complete this and then I will do your jobs, right? Likewise, that is called non-preemptive job, right? So uh, SJF, shortest job first, is optimal because it gives the time for a shorter jobs to run based on the availability of the jobs in the queue. So let's use this for an example, right? Let me give an example, please. Okay, so this is one example. I will come back to this theory next first while I will do explaining. Okay, so this is a example of non-preemptive SJF. Non-preemptive means while the job is running on the CPU, you cannot take that out. Okay, that is the non-preemptive shortest job first algorithm, right? So let's see how this goes. Listen carefully. I will only explain this one time, right? I might have to do it again, but I will explain it only one time. Then you have to read the, I mean, watch the recording again to see the replay. Okay. So first understand the columns, right? Process P1, P2, P3, P4. They are coming in order. Then there is an additional column saying arrival time. So which millisecond this job has arrived to the queue. Okay. So P1 comes at 0 millisecond. P2 comes at 2 millisecond, P3 comes at 4 millisecond, and P4 comes at 5 millisecond, right? That's the second column. And third column is called burst time. Burst time is time required to do the job. So we call it burst time. So P1 requiring 7 milliseconds, P2 requiring 4 milliseconds, P3 requiring 1 millisecond, and P4 requiring 4 milliseconds, right? So that is the one which is given. So based on this data, we have to draw a Gantt chart for a non-preemptive shortest job first algorithm, right? So non-preemptive means once the CPU time is given, you cannot take it out. Okay, so that's the definition. Okay, so let's go and draw this, right? So first we will think about the first process in the queue. It came at time 0, so no problem. So P1 actually came at time 0 and it has a 7 milliseconds time. So since this is non-preemptive, once the P1 is given the CPU at 0, it will finish at 7 milliseconds. Until such time, no matter where a shorter jobs comes, we are not worried about it, right? So after 7 milliseconds, P1 finishes, right? Then P2 came at 2 millisecond, P3 came at 4 millisecond, P4 came at 5 milliseconds. So all three processes are now in the queue, right? When the P1 finishes, because P1 finishes at 7. So P2 came at 2, P3 came at 4, P4 came at 5. So all three are there competing for the CPU. Now, the concept is shortest job first, right? So which one has the shortest time?
P3.
P3. So therefore, P3 is given next chance to run. So P3 out of these three, P2, P3 and P4 is given the CPU time. So P3 has only 1 milliseconds of burst time. Then from 7 to 8, P3 runs and finish. Right. Then in the queue, there are two jobs, P2 and P4. The problem is its burst times are equal, right? P2 also has 4 milliseconds. P4 also has 4 milliseconds. So our algorithm is shortest job first, but shortest job first cannot be applied because the time is same, right? දෙකේම 4යි තියෙන්නේ. Both has 4 milliseconds of burst time. So which one will run then? So then when the burst times are equal, right, we consider the arrival time, right? Which one came first? So P2 came first, then P4. So even though the burst times are equals at 4, P2 came first at time 2. So because of that, P2 will be given the time, right? So because of that, P2 is given 4 milliseconds of waiting time. Yeah, when the burst times are when you ask questions, ask actually at for the everyone mode, then others will also get to know the question. So one student is asking me when the non-preemptive work like first come first serve. No, actually, when the burst times are equal, non-preemptive turns into first come first served. Okay, when the burst times are equal, right? So when the burst times are equal, P2 and P4 4 milliseconds, then we consider the arrival time. P2 came first, so because of that, P2 given the next CPU time. So 8 to 12, P2 runs. Then finally, only P4 remaining. P4 is given the CPU time of 4 milliseconds. So the non-preemptive SJF Gantt chart will be P1 for 7 milliseconds, then P3, then P2 and P4. Then one student again asking why we put the P1 first. Because we have to see the arrival time, right? P1 at the time 0, P1 is the only process that is there. P2 haven't arrived, P3 haven't arrived, P4 haven't arrived. Right? Only the P1 is there in the queue, so it will get the first chance. That is why P1 first. Even though burst time is high, only the P1 is in the queue. So after running, 2 milliseconds only, P2 arrived. Okay. So that is why we ran the P1 first. So hope you understood this Gantt chart. I will explain this one more time. processes are coming in this order and their arrival time is given in the second column. Burst times are given in the third column. So when you take the process list, P1 arrived at time 7, others haven't arrived yet. So even though the burst time is 7, which is high, P1 given chance to run. Since the nature is non-preemptive, so in the middle we cannot change the CPU. Because of that, until the P1 completes, others have to wait. So the P1 runs and completes at time equals 7. So by that time, P2 has arrived, P3 has arrived at time 4, P4 has arrived at time 5. So there are the other 3 processes they are in the ready queue, P2, P3 and P4. Then we employ the shortest job strategy. So then we pick the shortest one. Shortest one is P3. So the P3 runs next. So 7 to 8, P3 runs. Then in the job, there are 2 remaining. So we are trying to get the shortest job. But P2's burst time equals 4. And P4's burst time also equals 4, which is equal. So we cannot take any decision. So because of that, we have to check on the arrival time. So P2 arrived first, then P4. Because of that, we allow P2 to run first, then P4 to run next, right? So that is how the Gantt chart is drawn. So let's calculate the waiting time. So P1's waiting time is how many milliseconds? P1 waiting time is P1 arrived 0. Yes, P1 arrived at time 0 and it was got the CPU at same time. So 0 minus 0 is 0. And P1 got that time. P2 arrived at time 2, got the CPU time at 8, right? So P2's waiting time is 8 minus 2. 8 is the CPU time got time and the 2 is the arrival time. So we calculate 8 minus 2, which is 6. Then for the P3, arrival time is 4 and got the CPU time at 7. So 7 minus 4. P3's waiting time is 3. Then P4, arrival time is 5. Got the CPU time at 12, right? So P4's waiting time is 12 minus 5, which is 7. So when you want to get an average, right? 0 plus 6 plus 3 plus 7 divided by 4, that is 16 divided by 4, which is 4, right? So the average waiting time is calculated like that. Have you understood the points? Right? තේරුණාද? හරි. Waiting time එක calculate කර හැටි. Did you understood how I calculate the waiting time?
Yes, sir.
Yes, sir, clear.
Right. Okay, clear. Right. So then we will calculate the turnaround time. Okay. Turnaround time. I will use the shorter form here because for easier for me to write, but don't use this abbreviation at the exam. You always write the longer form, turnaround time, right? So this is for the turnaround time, we will see how the calculation goes. For the P1, it arrives at time 0 and went out at time 7. So 7 minus 0 is 7 for the P1. For the P2, arrived at time 2 and went out at time 12. So the P2's turnaround time is 12 minus 2 is 10. And for the P3, arrived at time 4, went out at time 8, right? P3 went out at time 8. So 8 minus 4 is 4. And for the P4, arrived at time 5, exit at time 16. So 16 minus 5 is 11. So the turnaround times for 4 different processes are given here. So average is 21, 25, 32. Yes, 32 divided by 4, which is 8. 8 milliseconds is the average turnaround time. So then we'll calculate the response time. I will put that in here, this side. Right. So the response time for the P1, the definition is from arrival to the queue until you get the first CPU. So P1 arrived to the queue at time 0, got its first CPU at time 0. So for the P1 arrival response time is 0 minus 0 is 0. And for the P2, arrival to the queue at 2 milliseconds, got the CPU at 8 milliseconds. So 8 minus 2 is 6. And for the P3, arrival to the queue at 4 milliseconds, got the first CPU at 7 milliseconds. So 7 minus 4 is 3. And for the P4, arrived at 5 milliseconds, got the first CPU at 12 milliseconds. So 12 minus 5 is 7. So the average is 16 divided by 4, which is 4. So the average response time is 4. Right? For these all examples that I did so far, the average response time is equal to average waiting time. But we will take few examples where these two are different. Okay. So far you know how to do the calculation for preemptive non-preemptive shortest job first algorithm, how to do the Gantt chart, how to calculate the waiting time, how to calculate the turnaround time, and how to calculate the response time. Okay. Hope so far you got a clear idea. Is that so? Right? So far, okay? Any questions? Any questions? Okay, right. So then let's go forward. So we have to know how to do the preemptive shortest job first, right? So let me explain this again. I will do it slowly. Now, how do we draw the preemptive shortest job first algorithm based on the example given, right? So let's understand the columns. First column is the processors P1, P2, P3 and P4. Then the second column is arrival time of the each process. P1 arrives at time 0, P2 arrives at time 2, P3 arrives at time 4, and P4 arrives at time 5. And the burst times are also given. P1 7 millisecond, P2 4 millisecond, P3 1 millisecond, and P4 5 milliseconds. Right? So that is the data given to us. Then right. So then we will try to draw the Gantt chart for shortest job first algorithm with preemption. Preemption means you can interrupt a process at any time when there is a shorter job in the ready queue. Okay, so that's the definition. So let's draw slowly these diagrams. Right. Okay. So first at the time equals 0, right? P1 arrives. P2 and P3 and P4 haven't arrived yet. So only P1 is in the queue at time 0 and its burst time is 7. So we will start giving CPU time for the P1. Okay. So really, I mean, follow with me. So I am doing it slowly because I don't want to explain this again. Right. So P1 arrives at time 0. No others have arrived yet. Its burst time is 7. Right? So only job remaining in the queue is P1. So we will give the P1 time to run. So at time equals 0, we start with the P1. Right? Then P2 is coming at time, arrival time 2. So by that time, P1 has completed 2 milliseconds of work. Right? So P2 arrived to the queue. Right? P2 arrived to the queue with a burst time of 4. Right? Now, P1 originally had 7 milliseconds of work time. So it already started work at time equals 0 and completed 2 milliseconds of work. So how much P1 has remaining work? 5. Yes, 5. And P2 has work 4. So which is shorter than P1, right? P1's remaining time is 5 milliseconds, but P2's work, which is coming at 2, is 4 milliseconds, which is shorter than P1's remaining work. So because of that, shortest job has to be allowed because we use the preemption. Anytime you can interrupt. So what we do is we will stop P1 from running at the CPU and allow P2 to run. Right? Got the point? So on the Gantt chart, from the second milliseconds, we allow P2 to run. Okay? Right. By that time, I will do the annotation. By that time, P1 has 5 milliseconds of work remaining at time equals 2. P1 is having 4 milliseconds. So because of that, P2 starts running at from the time equals 2. Then, okay, system is running. Then at 4 milliseconds of time, P3 comes to the queue. So when P3 comes to the queue, we evaluate what are the remaining times, right? What are the remaining times? We will check. So when P3 comes, its burst time is 1. P1 has 5 milliseconds remaining. P2 has started from time 2 and it went up to time 4, right? So from so out of 4, P2 has only 2 milliseconds remaining work. However, P3 has only 1 milliseconds of remaining work. So because of that, we have to let the P2 go. Okay, stop working, and I want to run P3. Right. From the 4 millisecond, right? So right. P3 starts running from time equals 4. So it completes at time equals 5, P3. And P2 has 2 milliseconds remaining. Then P4 arrives at time equals 5. So out of there in the queue, P4 remaining 4, P2 remaining P2 remaining time is 2, P1 remaining time is 5, P4 remaining is 4, and P3 already completed. So out of these 3, now the shortest one is P2. Because of that, we allow P2 to run, right, from 5 to 7 until it completes, right? Then after that, we check again the queue. P4 has 4 milliseconds, P1 has 5 milliseconds. Therefore, we allow at 7 P4 to run because of 4 milliseconds of remaining time. So 7 to 11, P4 runs. At the end, 5 milliseconds of P1's work is remaining. So that is the only one remaining in the queue. So because of that, we allow P1 to run at the last. Got the point? Terunada? Do I have to explain again? Tell me. I can explain again if you want. Right.
Sir, explaining.
Right. Okay. So I will do it again. Right. So this is how it works. Right. So you understood the columns, right? P1, P2, P3, P4 comes. Arrival times are given. Burst times are given. Right. And then, so we'll start from the first one. Right. P1 arrived at time 0. It has a time of 7 milliseconds initially, right? So others haven't arrived yet. So we allow P1 to run. Okay, so from the Gantt chart, we draw, okay, P1 have started running. Then at time equals 2, P2 comes to the queue. So with the burst time of 4, right? So now we check with the one which is running and the one which is there in the queue, which one is the shortest one, right? So when the P2 arrives at time 2, P1 has already started doing its work, right? So total time is 7. However, at time equals 2, only 2 have completed, right? 2 milliseconds of work has completed. So out of 7, another 5 remaining, right? So the P1's remaining time is 5 and P2's burst time is 4, which is shorter, right? So because of that, we have to stop P1 from running and allow P2 to run. Is that understood?
Yes, sir.
Ekateruna? Yes. So then P2 is allowed to run, right? So then P2 have started work, right? So P1 is preempted. So P1 is waiting in the ready queue with the 5 milliseconds remaining. P2 has started work, right? Then another one comes. P3 comes at 4. Then we have to check again, right? So P2 has already started work with the 4 milliseconds. Now 2 have gone, 2 remaining for the P2, P1 remaining 5, right? P3 has burst time of 1. So out of these 3, P3 is the shortest one. So we take out P2 from the running and we allow P3 to run. Okay. So from the 4 millisecond to 5 millisecond, P3 is allowed to run, right? Then after P3 completed, so the time has gone to the 5th millisecond, right? So now P3 is already completed and went out, other 3 remaining, right? P4 has 4 milliseconds of burst time, P2 has 2 milliseconds because 2 has completed, P2 has 2 milliseconds, and P1 has 5 milliseconds. P4 has 4 milliseconds, right? So which one is the shortest? P2. So because of that, P2 is allowed to run. Is that clear? එතෙන්ට එනකම්? Yes, yes, okay, right. So then P2 completes at 7, so P2 also gone out. Now in the queue, P1 with 5 milliseconds, P4 with 4 milliseconds. So the shortest one is P4. So we allow P4 to run. So at 11th millisecond, P4 completes. Then only remaining one is P1 with 5 milliseconds. So we allow P1 to run, right? So, and finish at 16 milliseconds. So now the preemptive Gantt chart is complete. Now I think you have understood how to draw it. How I made the decisions. තේරුණාද? Is that Gantt chart is clear now? Yes. Okay. Right. Then let's calculate the waiting times. Right? Now in this example, I am going to tell you the definition, then we do the calculation. Okay. So waiting time, let's calculate one by one. Right. So the first we take the P1. Right. We calculate the waiting time. Waiting time. So P1, when P1 comes to the queue first, right? Then it got the CPU time. So the initial waiting time is 0. Right. But after second millisecond, right, it has to wait, right? Wait until 11th millisecond. See, P1 initially waiting time is 0. But after the second millisecond, P2 was put back to the ready queue and waited. And only after 11th millisecond only it got the CPU time again. So it has to wait from second millisecond to 11th millisecond, that is 11 minus 2. Then only that its total waiting time is calculated. So its total waiting time is, even though initially 0, later it has to wait from 2 to 11. So that is 9. 9 milliseconds of waiting time for P1. Is that clear to you? තේරුණාද? P2 ට P1 ට කොච්චර වෙලාවක් බලන් ඉන්න උනාද? How many milliseconds P1 has to wait in total? Is that clear?
Clear, sir.
Right. Then P2. Yes. We'll take P2. We do one by one. Simple as that. Right. P2 comes to the queue at time equals 2. As soon as it comes to the queue, it got the CPU time. So initial waiting time is 2 minus 2. So it's 0. Initial waiting time is 0. Right. After 4th millisecond, P2 has to wait until 5th millisecond. So that is from 5 minus 4, P2 has to wait. So P2's total waiting time is 1 millisecond because 5 minus 4, 1. And initially it was 0 milliseconds. After 4th millisecond, it has to wait until 5th millisecond to run again. And after that, it completes. So P2's waiting time is 1 millisecond altogether, right? Then, is that clear? P2's waiting time?
Yes, sir.
Yes, sir.
Right. For the P3, again we'll check. Okay, P3 arrived at time equals 4, right? And it got the CPU time as soon as it arrived, and P3 has complete. So P3 has no waiting time, so its waiting time is 0. So somebody is asking, can you explain the P2's initial waiting time? So initial waiting time is this. P2 arrived at time equals 2, right? And it got CPU at the same time, right? So that is why I put 2 minus 2. Arrived at 2, given the CPU at 2. So 2 minus 2 is 0 actually. Initial waiting time is 0. Then after 4th millisecond, P2 has to wait. So that is why 5 minus 4 is given. So is that okay? Right?
Yes,
P2, oh yeah, right. Then P3's waiting time is 0 actually because it came at 4, got the CPU time at 4. This is actually 4 minus 4, that is 0. And then P4 came to the queue at 5 millisecond, right? Got the CPU at 7 millisecond, right? So 7 minus 5. Afterwards, there is no other waiting time because P4 completes at 11. So the P4's waiting time is 2, right? So the waiting times, total waiting times are calculated like this for the P1, P2, P3, and P4. Then average waiting time is 9 plus 1 plus 0 plus 2 divided by 4. That is 12 divided by 4, 3. So this is the average waiting time for preemptive shortest job algorithm for the given question. Is that clear? පැහැදිලිද? Right. මේක calculate කරපු හැටි තේරුණාද? එකින් එකට calculate කරන කොච්චර වෙලාවක් බලන් හිටියද? How much time it has waited in the queue from initial admission until its end. So we simply do the calculation. මේ Gantt chart එක බලාගෙන හදුවා හැකි. You don't have to do, do lot of math. You just simply watch the Gantt chart. If you have drawn the Gantt chart correctly, then simply from the Gantt chart you can do the calculation. Initial time 0, given CPU time 0. So that is why 0 minus 0, P1's initial waiting time is 0. Then afterwards, at 2, P1 has stopped working. Then only at 11, it got CPU time again. So 11 minus 2, we got 9. So total waiting time for P1 is 9. Likewise, using the Gantt chart only, we do the calculation, right? If you do like that, it is very easy. Gantt chart එක හරියට ඇඳලා you draw the Gantt chart correctly. Then using the Gantt chart, we do the calculation. හරි? Waiting time okay? පැහැදිලිද?
Okay, sir.
Okay. Right, let's do the turnaround time. Huh? Okay, I use a different color. Turnaround time. Turn around time. Okay. Let's first do the P1. P1. Okay. P1 came to the queue at time 0. Right? And P1 went out of the system at time 16. So 16 minus 0 is the turnaround time for the P1, which is 16. And for the P2, P2 came to the system at time equals 2. P2 went out of the system at time equals 7. So 7 minus 2, 5 for the P2. P3 came to the system at time equals 4. Went out of the system at time equals 5. So 5 minus 4, which is 1. And P4 came to the system at 5 milliseconds. Went out of the system at 11 milliseconds. So 11 minus 5, which is 6. So average turnaround time is, we add together and divided by 4. So if you add together 12 plus 16, 28 divided by 4 is 7. So 7 milliseconds is the average turnaround time for the preemptive SJF algorithm, this example. So let's do the response time. And one student have asked, what is the difference between waiting time and the response time? And I have given told it 3 times. I am saying for the fourth time now. So the difference between waiting time and the response time is, response time only calculates from the admission queue until it gets its first CPU time. පළවෙනි CPU time එක එනකන් බලන් හිටි වෙලාව විතරයි. The waiting time until it gets the first CPU is the response time. Okay, but the waiting time is the total waiting time. That means from the admission to the queue until it goes out, how many milliseconds of waiting happened in the queue. එතකොට මුල ඉඳලා අගටම කොච්චර බලන් හිටියද කියන එක තමයි waiting time කියන්නේ. ඕක තමයි වෙනස. From admission to the end, the time waited in the queue is waiting time. From admission until first CPU time is the response time. හරි. Then let's calculate the response time. So as response time we are going to calculate. Right. So the response time.
Sir, excuse me.
Yes.
How P4's arrival time is 5?
Here, arrival time is 5 here given. Here, see.
P3 also 4, no?
P3 also 4.
Mm.
Yes. Yes. Right.
We can looking that chart.
In chart, P3 arrival time is 4. See.
That's why that's the way how P4 is 5.
P4 is 5. Arrival time is given is here, no. Arrival to the queue. But when the CPU time is given, only here we can give the time. When the CPU time is given to the particular job, we mention it here. We start drawing mentioning it from here. But arrival time is arrival to the ready queue. That is, in the system. When that happens, only we can consider giving the CPU time. So that is two different things. Arrival time is when the job comes to the queue. ඒ කියන්නේ queue එක කියලා කියන්නේ pay එළියට ආවහම queue එක when somebody comes to the queue, that is called arrival time. But when he is served, right? When that particular person is served, say food or something, that is called CPU scheduling time, right? So that is mentioned in the Gantt chart. Now that is, you don't get confused, okay? Arrival time is arrival to the queue, but in the Gantt chart we draw the time that we got the CPU. තේරුණාද? CPU එක වෙලා CPU එක හම්බෙච්ච වෙලාව තමයි ගන්නෙ. We get the CPU time, which time we got the CPU. Okay? Is that clear? පැහැදිලිද? Is that clear? So don't get
Yes,
confused.
sir. Thank you.
Right. Don't get confused, huh? Arrival time, you don't get confused with the CPU. I mean, the time it got the CPU. It is mentioned in the Gantt chart. Right. So now the response time we have to calculate. So first one, we'll take about the P1, right? P1 first came to the system at time 0 and it got its first CPU at time 0. So P1's response time is 0 minus 0, which is 0. So response time is the time we got the first CPU, so we don't consider the other times. පස්සේ wait වෙච්ච ඒවා අපි ගණන් ගන්නෑ. We are not considering the waiting times after, some time. We are only considering the waiting time until it gets the first CPU. So for the P1, it immediately got the CPU, so its response time is 0. For the P2, arrived at time 2 and got the first CPU at time 2 also. It haven't waited P2 also. So P2's waiting time is 2 minus 2, again 0. So we won't consider the other waiting times. So initial waiting time only we consider from arrival to the queue until it gets the first CPU. So P2 gets first CPU at time equals 2. So 2 minus 2 is 0. And for the P3, arrived at time equals 4 and it got first CPU at time equals 4. So 4 minus 4, again 0. So the P3 got its first CPU on the arrival. So it haven't waited. So because of that, response time for the P3 is also 0. And for the P4, arrived to the queue at 5 and got its first CPU at 7 here. So 7 minus 5 equals 2. So the P4's response time is 2, right? So we don't consider the other waiting times, and the average response time is 2 divided by 4, that is 0.5. Right. Now, see the difference. Here, the total average waiting time is 3, but average response time is 0.5, right? So that is why the difference. The waiting time means the total waiting time from admission until it goes out. But for the response time, we only calculate the initial waiting time from admission to the queue until it gets the first CPU. Now, do you understood the difference between the response time and the waiting time and how I did this calculation? මේක කරපු හැටි තේරුණාද? Did you got the understanding?
Yes, sir.
Yes.
Yes.
Right. So that's about the preemptive SJF, right? So hope that now we have learned three, actually two algorithms. One has two variations. Okay. So cat one is 12. I think, yeah, 12. 1 to 2. The PDF that you got over the mail. So everything up to that point, you get the first cat, right? So because of that, now let's see. So we have learned about. So I have to clear this. We have learned about. Right. So then let's. Yes, I have given you the explanation. So there are some questions you can work out from the past cat papers, and you post in the Telegram group, and the others can respond. So that is how you learn, right? So Taraka has raised hand. Who is Taraka? So you can ask the question. Okay, it may be accidental. So if you want to have ask question, you can ask, right? So that these areas I have given ample examination questions are there in the cats. What you can do is based on the day school, you watch the day school and you do the math, right? Draw the Gantt charts and post it in the social media or a discussion forum, right? Then the others can respond, right? How this is happening and all. I want that discussion. After that only I will answer. Okay? Don't send me email saying that whether this is correct or not. No, you work out the question, you post it in the group, and others should respond, right? Whether it is correct or not. You can. So when I see the discussion only, I will okay, say this is correct or this is wrong or whatever, right? So that is how I encourage the discussion, and they don't send me individual mail saying that, sir, whether this is correct or not, because I don't have much time to respond for all those. So you post it in the group. Okay. So there are about, I mean, from 2000, I think 11 onwards, you have past questions for this kind of things. Even in the final, you have the questions. So you can do work. Yes, there are ample examples. Right. So next one, we will explain the missed slides, right? So the priority of the process. So now when this particular weight, the burst time is equal, right? We employ the strategy of first come, first serve, right? When the burst time is equal in the first non-preemptive algorithm or SJF algorithm, that we have employed the first come, first served mechanism. Uh, However, there are some places where in the question you can see the priority, right? So when there's additional column has giving a priority and with a priority number. So when that sort of column is given with the priority, you have to use the priority, not the first come first served order, right? That's all I have to say regarding the priority. So when this priority is needed, because sometimes in the real world this kind of a problem can come. Now, for example, supposing you are trying to photocopy a book, right? And you came early in the morning to the queue, right? So the photocopy man starts doing your photocopying at the morning. So you are happy that okay, you came first to the queue, that you are working. Then after some time, one guy comes with the 2 pages. Okay, he will ask you, can I have only 2 pages? No, can you give me the time? So you gleefully agree. Okay, let that guy do the job. So 2 pages done, go on. Now photocopy man again, like CPU, does your work, right? Then again another person comes. He says, I have only 1 page. Can I be allowed? We allow. Likewise, again, these shorter jobs keep on coming so that your job doesn't go forward, right? Short jobs keep on coming, and preemption, because of preemption, short jobs are always going. So when that kind of thing happens, long running jobs will starve the CPU time, that it doesn't get the CPU time, because always short jobs are coming, right? When that happens, long jobs have to somehow continue, right? So because of this, the concept called aging has uh, introduced. Now we call it indefinite blocking, we call it starvation. Starvation is we don't get the CPU time. So when you get the CPU time, it's like food. So we don't get the CPU time, so we tend to starve. That means අපි බඩගින්නේ ඉන්නේ. So we tend to starve. So we call it starvation. So because the shorter jobs comes, CPU is given for the shorter jobs, and longer running jobs, it doesn't get the CPU because of this algorithm's nature. So when this kind of thing happens, there is a solution. So after some time, so you add some priority to the longer running jobs. So okay, you have waited for the queue, so you get some points, say, right? So we call it aging, right? එතකොට වයසට යනවා. ටික 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 you call give a points to the time you spend on the waiting, right? When sometimes have elapsed, the priority of that longer running job will increase than the shorter running jobs which is coming. So when that happens, the longer running job has to run, shorter running jobs has to wait. Okay, now for the photocopy man will say, okay, this guy has waited in the queue for this long time, so I cannot keep him waiting forever. So I want his job to finish before, accommodating any more short jobs, right? So, right. So because of that, we need to do it. So this aging concept introduced to help alleviate this problem of shorter running jobs, coming and bombarding the longer running jobs and preempting, and so that the longer running jobs doesn't get the CPU time, right? So that's all. Now then that priority of a process is implemented. 0 is the highest, 15 is the lowest. This is for the Unix, but when at the exam, if I give you that sort of questions, I will always give which, which number is the highest, which number is the lowest. So you can get the priority, right? So then there is a question, sir, the OBT day of 6th of the September from 4 to 5 p.m. confirmed. The according to the current timetable, it's the Cat 1, so it's not OBT, right? It's an NBT. We don't have OBT for this particular subject, we only have 2 NBTs. That's all. Right? Always refer the master timetable cat window. And if there is a change, we will inform. Okay? Right. Then the final one is called round robin algorithm. It is the most suitable scheduling algorithm for a time sharing system. So that means now you know that the problem associated with shortest job and the longer running jobs and all. So 2 algorithms we have learned. First come, first served, shortest job first. Shortest job first has 2 variations. One is called non-preemptive, right? Uh, and preemptive. So I have explained 2 examples of non-preemptive and preemptive. And the question is asked, how can you explain how to calculate highest and lowest priorities? Actually, it is given. You don't have to calculate any, right? The priority number is given. So, and I have given, I will give you at the exam, okay, which one is the highest and which one is the lowest. So then priority, based on the priority number, you can, you know, which one has to be given CPU time. So I will give that. So don't worry, right? And final one is called round robin. So round robin is sort of this robin is a small bird, right? So it generally goes around places and it comes back to the same place where it started. So that is why it's this particular algorithm is named as round robin. So what it does is, instead of giving priorities, shortest jobs and all those things a time, what it does is it gives all the jobs in the queue equal time to run, right? For example, now I will give 5 milliseconds of CPU time for all the jobs in the queue, right? So when that happens, every job has to make use of that 5 milliseconds given to it, run within that 5 milliseconds, and if there is more time needed, it has to wait until it gets the next round of 5 milliseconds, right? So that's all. It's actually a basic FCFS with the preemptive time slicing. So time slice is defined as a small unit of time. So you give a time for everybody, right? So then this no priority business, nothing will happen. So based, when you get the time slot, you can run. So that's about the round robin algorithm. So let me open the with that round robin algorithm. uh, I will show an example and then we can wind off the class today. Give me a second until I open that. Let me share this. Can you share see my screen? Can you see my screen?
Yes, sir.
Yeah,
Yes, sir.
right. So now this is one example of the round robin algorithm. And take this, right? So this round robin algorithm the job 1 is needing 20 milliseconds of burst time, job 2 4 milliseconds, job 3 3 milliseconds, job 4 3 milliseconds. The time quantum, that is the time slot, is 4 milliseconds given. So the 4 jobs are there, and first come first served timing is given. So I will take the annotation and draw the Gantt chart, right? So now we'll start from time 0, right? And first 4 millisecond slots are given. So from 0 to 4, right? The job 1 came first. So the J1 will given the CPU time, right? Then after 4 milliseconds, the next slot, 8 milliseconds, that is next slot is given to the next job, right? So the job 2 4 milliseconds, so job 2 runs, right? It's using the first come first served order. Then the next one, job 3, only 3 milliseconds needed, so no need of having 4, so only 3 milliseconds needed for the job 3, it will finish up. And then the job 4, again 3 milliseconds needed. So job 4 runs until 14. Then another 4 milliseconds are given for the, now all the job 2, job 3 and job 4 finish, only job 1 remaining. So the remaining time slots, everything will be given for the job 1, right? So 18 likewise until 220, so that means for 16, so until 30 the job 1 runs and finish. So it is pretty easy, the round robin, so no big hassle, right? Time quantum is given, first come first served basis, we give out the slots, and we draw the Gantt chart like this, right? So it is pretty easy. Then the waiting time, the response time, everything can be calculated based on the Gantt chart, right? So if you take waiting time for the job 1, J1, waiting time, initially it was 0. Then from 4 to 14, it waits. So that is 14 minus 4. Right? So altogether it's 10 milliseconds waiting time for the J1. After that it runs continually. And for the job 2, initially came at 0, got the CPU time at 4. So 4 minus 0, that is 4. Job 2, 4 milliseconds. Job 3 initially came at 0, but got the CPU time at 8. So 8 minus 0, the waiting time is 8. And job 4 came at 0, got the CPU at 11. So 11 minus 0 is the waiting time for job 4. So altogether 21, 29, 33. 33 divided by 4. This is the average waiting time for this entire system. So similarly, you can calculate turnaround time and the response time. So this is pretty easier than the shortest of first algorithm. You get a time quantum, and based on the time quantum, you give out the CPU time. If the job's burst time, this is the time required, is shorter than the quantum, then you only give the required burst time like this. See, from 8 to 11, job 3 only 3 milliseconds. So we are not going until 12. We are finishing at 11. Then for the job 4 also 3 milliseconds. Out of 4 milliseconds time, only 3 needed. So 11 to 14 we calculate. Then afterwards we can give another that time quanta, right? So this this one, the Gantt chart I will explain again how I have drawn, right? You have the job 1, job 2, job 3, and job 4 in the queue, and the time quantum is 4. So we start from 0. The job 1 came first, so first 4 milliseconds will be given for the job 1, like this. Then next 4 milliseconds, we give it to the job 2 because it's next on the queue, right? Because time quantum, each time every job we will try to give 4 milliseconds. That's all. And for the job 3, the next quantum is given. So job 3, only 3 milliseconds needed out of 4. So 4 is given, only 3 needed. After that it completes. So because of that, 8 to 11 is drawn, not the 8 to 12. So 8 to 11, J3 completes. Then next 4 milliseconds is given to the job 4. Then it again requires 3. So 11 to 14, 3 milliseconds given. And that's all. And then after J4 completes, all 2, 3, 4 completes, and job 1 is given the rest of the time, 4 by 4 each. So that's all, right? Hope you understood this concept. With that, I will wind up the class for today, right? I will inform you through the LMS if there is an additional day school with the time. So otherwise, we will stick to the schedule and put an additional day school at the end. Okay. So if there is 1 day school in between, I will inform you by uh, seeing the master timetable so that there won't be any clashes. Okay. With that, I hope you understood this round robin and 3 examples that I did. Hope that you would do as I have told you. Work out the questions because there is a definite question coming for the cats. So work out the past questions and uh, then you will do. Yes, I will upload the day school recording and since I am doing it at home, so please give me time until tomorrow. By tomorrow, I will upload the day school recording. Okay, right. Right. So hope everybody got some idea and work out the questions, post it in the group, right? And the students who haven't got enroll to the group, this under the course information, you have this Telegram group link. So uh, ask your colleagues to use that link to join the Telegram group. Okay, because when I have sent this out open, then somebody have shared it in the other forums, and people who are not I mean members of the group and try to share this explicit materials to the group. So I had to close the group. Otherwise, I kept it open. Generally, for the last few batches, I kept it open. Everybody could register at any time, but this time, of course, because of the misuse, I have to close. So now people who are, you don't give out the links out, you ask all the colleagues of you to log into the LMS and obtain the link. Unless if you are sure of your friend is doing the class, you can share it. Otherwise, please don't. Okay. Yeah. There's a direct message. Yes. J1 is coming. Yeah, right. J1 4 milliseconds, then J4 from 14, right? From 14 to 18, 18 to 22. Likewise. Yes. Yes, you can afterwards you can directly draw, no problem. Yeah. From 14 to 30, if you draw it like that, you get full marks. No problem. Yeah. You don't have to divide the slots. Yeah. Okay. So that's all. I will wind up the class now. Thank you very much. Today we had the marathon session. Okay. I hope we will have a good session next time also. Then we can, complete as much as possible needing for the cat one. Okay. Otherwise, I will give you an additional class. Right.
Thank you very much, sir.
Yes.
Thank
Yeah.
you so
Yeah.
much, sir.
Yeah. Yeah. Okay. I will close the class now.